March 30th, 1939. The sleek silver fighter streaked across the German countryside at a speed that would have shattered every aviation expert's expectations. Test pilot Hans Dieterle gripped the controls of the Heinkel HE-100 as the specially modified aircraft reached 746.6 km per hour, obliterating the previous world speed record by 37 km per hour. This wasn't just another incremental improvement in aviation technology. This was a quantum leap that demonstrated German engineering supremacy to the entire world. Yet within hours of achieving this stunning triumph, the HE-100's fate was already sealed. Despite proving itself faster than any fighter aircraft in existence, despite outperforming the legendary Messerschmitt Bf-109 that formed the backbone of the Luftwaffe, this revolutionary machine would never enter mass production. The aircraft that could have changed the course of aerial warfare became instead one of history's greatest missed opportunities, a technological marvel relegated to propaganda duties, while inferior designs fought the battles it should have dominated. The story begins 5 years earlier in the offices of Ernst Heinkel, where the bitter taste of rejection still lingered from the fighter competition of 1934. The Reich Air Ministry had chosen the Messerschmitt Bf-109 over Heinkel's HE-112, a decision that stung the proud aircraft manufacturer who had supplied virtually every fighter for Germany's nascent Luftwaffe. Rather than accepting defeat gracefully, Ernst Heinkel became obsessed with proving his company could build a fighter so superior that the Air Ministry would have no choice but to order it into production. The genesis of what would become the HE-100 emerged from this burning desire for vindication. Walter Günther, the brilliant designer behind many of Heinkel's successes, studied the limitations that had doomed the HE-112 and resolved to create something entirely new. The existing design had reached the end of its development potential, burdened with complex construction that required 26,164 rivets and nearly 3,000 individual parts. Günther's new project, 1035, would achieve the seemingly impossible, 700 km per hour, while being dramatically simpler to manufacture. The revolutionary approach showed immediate results. Where the HE-112 required over 26,000 rivets, the new design needed only 11,543. The part count dropped from 2,885 to just 969 unique components. Otto Butter, responsible for wing construction, calculated that these changes would save an astonishing 1,150 man-hours per wing assembly. This wasn't just evolutionary improvement, it represented a fundamental reimagining of fighter aircraft construction principles. Tragedy struck on May 25, 1937, when Walter Günther died in a car accident before seeing his masterpiece take flight. His twin brother Siegfried inherited the project, completing the final design specifications with Heinrich Hertel, a structures specialist who ensured the aircraft could withstand the enormous stresses of high-speed flight. By October's end, the complete design package reached the Reich Air Ministry, including detailed prototype specifications, delivery schedules, and costs for 3 aircraft destined for the Rechlin Test Center. The HE-100 that emerged from Heinkel's Marigny factory was a masterpiece of aerodynamic refinement. Every surface had been sculpted to minimize drag, from the completely retractable landing gear to the tightly fitted engine cowling that gave the aircraft its distinctive slab-sided appearance. The Daimler-Benz DB6-01 engine was mounted directly to the strengthened forward fuselage rather than on conventional engine bearers, saving weight while reducing frontal area. Exhaust ejectors provided additional thrust, while the supercharger inlet was relocated from the engine, cowling to the wing's leading edge for cleaner airflow. But the HE-100's most revolutionary feature lay hidden within its wings and fuselage, an evaporative cooling system that promised to eliminate drag entirely while reducing weight dramatically. This technology, previously tested on the experimental HE-119, represented the cutting edge of cooling system design. The concept was elegantly simple, yet mechanically complex. Engine coolant was heated under pressure to 110 degrees Celsius without boiling, then released into a network of tubing beneath the wing's leading edges, where it instantly flashed to steam. The cold airflow condensed this steam back to water, which was then recirculated to the engine. The physics behind evaporative cooling offered compelling advantages. Raising water temperature 60 degrees from 180 to 240 Fahrenheit absorbed far more energy than conventional cooling systems could manage. This meant smaller, lighter cooling infrastructure with zero aerodynamic drag penalty. During a demonstration flight in France, the system proved so effective that the wings became too hot to touch, burning the fingers of impressed French officers who tried to examine the aircraft after landing. The HE-100V1 took to the skies on January 22, 1938, just 1 week past its promised delivery date. The results were immediately apparent. This was the fastest fighter aircraft in the world. Test pilots recorded speeds that exceeded every existing fighter by substantial margins, performance that vindicated Ernst Heinkel's faith in his engineering team. At sea level, the HE-100 reached 560 km per hour, faster than the Bf-109E's maximum speed at any altitude. At 2,000 meters, it achieved 610 km per hour, reaching a peak of 669 km per hour at 5,000 meters altitude. However, exceptional speed came with significant drawbacks that would plague the HE-100 throughout its development. Luftwaffe test pilots complained about the high wing loading that resulted in dangerous landing speeds, forcing them to use brakes until the final 100 meters of runway. Ground crews despised the tight engine cowling that made maintenance extremely difficult, requiring hours to access components that could be serviced quickly on conventional fighters. Most critically, the revolutionary cooling system proved temperamental and failure-prone, with pump failures ending flights prematurely despite pilots learning to ignore warning lights. The world speed record attempt became Ernst Heinkel's ultimate statement of his fighter's superiority. On June 5, 1938, Ernst Udet flew the HE-105-2 to a new 100-kilometer closed-circuit record of 634.32 km per hour. This wasn't the dramatic straight-line dash planned for absolute speed supremacy, but it demonstrated sustained high-speed performance that combat aircraft would actually need. Significantly, Udet achieved this record using a standard DB601A engine, proving the HE-100's basic airframe was inherently faster than anything else flying. The absolute speed record required more extreme measures. The HE-100 V8 received clipped wings, a streamlined canopy, and most critically, a special DB601R engine that generated two 1010 kilowatts of power. This power plant was essentially a controlled explosion designed to last exactly 30 minutes, just long enough to set the record. On March 30th, 1939, Hans Dieterle piloted this modified machine to 746.6 km per hour, a speed that wouldn't be exceeded by piston-engined aircraft for decades. Yet even as newspapers proclaimed German aviation supremacy, the HE-100's production hopes were crumbling. The Reich Air Ministry had already decided that Germany would not support multiple fighter types using the same engine. The DB601 was in critically short supply, with Daimler-Benz unable to meet existing demands for the Bf-109 and Bf-110 programs. Every available engine was committed to Messerschmitt production, leaving no capacity for Heinkel's superior fighter. The ministry offered Heinkel a compromise: adapt the HE-100 to use the Junkers Jumo 211 engine, which was more readily available. This proposal revealed fundamental misunderstanding of the HE-100's design philosophy. The aircraft's entire structure was tailored around the DB601's dimensions and cooling requirements. Converting to the Jumo 211 would have required complete redesign of the engine mounting, cooling system and airframe integration. Most crucially, the early Jumo 211 lacked the pressurized cooling capability essential for the HE-100's evaporative system. Even if the conversion had been technically feasible, the resulting aircraft would have been significantly slower than the DB601 version, negating the HE-100's primary advantage over the Bf-109. Heinkel calculated that a Jumo-powered HE-100 would be inferior to the existing Messerschmitt fighter, making the entire development effort pointless. The company abandoned the conversion project, effectively ending the HE-100's production prospects. Political factors also influenced the HE-100's fate, though their exact impact remains debated. The Reich Air Ministry had implemented a rationalization policy that assigned specific roles to different manufacturers. Messerschmitt would build fighters, while Heinkel concentrated on bombers. This division of labor reduced competition and simplified logistics but eliminated opportunities for superior designs from secondary manufacturers. Some historians suggest this policy was designed to protect Messerschmitt's position, though evidence for deliberate sabotage remains inconclusive. The Bf-109's combat record provided additional justification for maintaining the status quo. By 1939, Messerschmitt fighters had proven themselves in the Spanish Civil War, establishing combat credibility that the untested HE-100 couldn't match. The Bf-109 was already in mass production with established supply chains and trained maintenance personnel. Switching to the HE-100 would have disrupted this system during Germany's military build-up, a risk the Air Ministry was unwilling to accept. Yet the most damning factor in the HE-100's rejection was the fatal flaw hidden within its revolutionary cooling system. The evaporative cooling that made the aircraft so fast also made it catastrophically vulnerable in combat. Traditional fighters had centralized cooling systems protected by armor and redundant plumbing. The HE-100's cooling system was integrated throughout the wing structure, creating multiple failure points that couldn't be armored without negating the weight savings that made the system attractive. Even minor combat damage to the wings could cause catastrophic coolant loss, forcing immediate landing or engine seizure. Rifle-caliber bullets that would merely puncture conventional aircraft could disable the HE-100's cooling system completely. During a combat scenario, this vulnerability would have proven fatal. The aircraft that was too fast to be caught could be destroyed by the lightest defensive fire, making it unsuitable for the brutal realities of aerial warfare. The HE-100's production run ended at just 12 aircraft, plus several prototypes. These survivors found an ignominious fate as the Heinkel factory's private defense force, flown by company test pilots who never encountered enemy bombers. The aircraft that should have dominated European skies instead sat in hangars, too valuable to risk and too few to matter. As the war progressed and Allied bombing intensified, these factory defenders remained grounded while inferior fighters bore the burden of Germany's aerial defense. Propaganda became the HE-100's final role, a task it performed with devastating effectiveness. Joseph Goebbels' ministry orchestrated an elaborate deception, using the 12 production aircraft, photographing them with different paint schemes and markings to suggest vast numbers of operational fighters. These images, published in German newspapers and aviation magazines, depicted the mythical HE-113 as Germany's newest superfighter, ready to sweep Allied aircraft from the skies. The deception succeeded brilliantly. British intelligence spent years tracking imaginary HE-113 squadrons, convinced the Luftwaffe was holding back its best fighters for a crucial moment. RAF pilots reported encounters with the non-existent superfighter throughout the war, usually misidentifying other German aircraft or even British Spitfires glimpsed at extreme ranges. This phantom menace influenced RAF tactics during the Battle of Britain, as Air Marshal Hugh Dowding insisted on maintaining reserves to counter the expected HE-113 deployment. By 1944, Germany's desperate situation prompted consideration of advanced fighter designs to counter Allied air superiority. The Project 1076 represented Heinkel's attempt to resurrect the HE-100 concept, with improvements addressing its original weaknesses. This new design featured a longer wing optimized for high-altitude interception, swept forward 8 degrees for improved performance. The cockpit was pressurized with a bubble canopy hinged sideways rather than sliding rearward. Most significantly, the evaporative cooling system returned, suggesting Heinkel hadn't learned from the original's vulnerability. Planned armament for the Project 1076 reflected the desperate circumstances of Germany's late war period. One 30mm Mk103 cannon, firing through the propeller hub, supplemented by 2 wing-mounted 30mm Mk108 cannons. This massive firepower was intended to destroy Allied bombers with single bursts, compensating for the limited ammunition capacity imposed by the aircraft's compact design. 3 engine options were considered, the DB603M producing 1,825 horsepower, the DB603N generating 2,750 horsepower, or the Junkers Jumo 213E rated at 1,726 horsepower. Performance projections for the Project 1076 were extraordinary, with the DB603N version expected to reach 880 km per hour. This speed would have matched the Messerschmitt Me-262, jet fighter then entering service, representing unprecedented performance for a piston-engined aircraft. Even with the more conservative DB603M, the projected top speed of 855 km per hour would have exceeded any Allied fighter by substantial margins. These projections were almost certainly optimistic, reflecting Heinkel's historical tendency to overestimate performance figures. Propeller efficiency decreases dramatically as blade tips approach the speed of sound, limiting the benefits of additional engine power. The advanced contra-rotating propeller planned for the Project 1076 might have partially addressed this limitation, but fundamental physics would have prevented the claimed performance levels. The design received low priority and remained incomplete when Germany surrendered in May 1945. International interest in the HE-100 validated its advanced design concepts even as Germany rejected it. The Soviet Union purchased 6 surviving prototypes for study, particularly interested in the evaporative cooling system they had experimented with on their own IL-21 project. Japanese representatives were equally impressed, acquiring 3 pre-production aircraft plus manufacturing licenses for 1.2 million Reichsmarks, with additional payments for tooling and technical support totaling another 1.6 million Reichsmarks. Japan's plans for HE-100 production reflected their desperate need for high-performance interceptors. The Imperial Navy designated the aircraft AX-HE-1 and planned immediate production as a land-based interceptor. Hitachi won the manufacturing contract and began construction of a dedicated factory in Chiba, but the complete tooling and technical drawings never arrived from Germany due to wartime transportation difficulties. The 3 aircraft that reached Japan were extensively tested and influenced subsequent Japanese fighter development, though direct production never materialized. The HE-100's legacy extends far beyond its brief operational history. The aircraft demonstrated that conventional thinking about fighter design could be transcended through innovative engineering and aerodynamic refinement. Its speed record stood as proof that properly designed piston-engined fighters could achieve performance levels previously thought impossible. The evaporative cooling system, despite its combat vulnerabilities, represented a genuine breakthrough in thermal management that influenced post-war aircraft development. Modern analysis reveals the HE-100 occupied a unique position in aviation history, too advanced for its time, yet fundamentally flawed for its intended purpose. The aircraft that was faster than anything flying proved that speed alone doesn't guarantee success in military aviation. Combat survivability, maintainability, producibility, and logistical support matter more than raw performance numbers. The HE-100 excelled at setting records but would have failed at winning wars. The tragedy of the HE-100 lies not in its rejection by the Luftwaffe, but in the missed opportunity it represents for aviation advancement. Had the cooling system vulnerabilities been addressed, had alternative engines been properly developed, had political considerations not intervened, the HE-100 might have evolved into the world's premier fighter aircraft. Instead, it became a technological dead end, its innovations abandoned rather than refined. Ernst Heinkel's obsession with beating Messerschmitt ultimately produced one of history's most impressive failures. The HE-100 proved his company could build the fastest fighter in the world, but it also demonstrated that engineering excellence without strategic thinking leads to magnificent irrelevance. The aircraft that broke speed records couldn't break through the practical constraints of wartime production and combat requirements. Today, no HE-100 survives to demonstrate its revolutionary design. The aircraft that promised to change aviation history exists only in photographs, technical drawings, and the testimony of those who witnessed its brief moment of glory. A full-scale replica at the Plains of Fame Air Museum in Chino, California, offers the only opportunity to appreciate the HE-100's elegant proportions and advanced design concepts. The HE-100 story serves as a reminder that technological superiority means nothing without the support systems necessary for practical implementation. The fastest fighter of 1939 became a propaganda tool because its revolutionary cooling system made it too vulnerable for combat. Its advanced engine was too scarce for production, and its late arrival made it strategically irrelevant. Speed records and engineering brilliance couldn't overcome these fundamental limitations. In the end, the Heinkel HE-100 achieved immortality not through combat success, but through its role as aviation's greatest what-if story. The aircraft that could have dominated the skies instead became a symbol of missed opportunities and the gap between theoretical performance and practical utility. Its 746 km/h speed record stands as a monument to German engineering excellence and a cautionary tale about the difference between building the fastest aircraft and building the right aircraft. The HE-100 was simply never meant to fight. It was meant to fly fast, set records, and prove Ernst Heinkel's genius to the world. In this limited role, it succeeded magnificently, achieving speeds that wouldn't be matched for decades while demonstrating innovations that influenced aviation development long after its brief career ended. But when Germany needed fighters that could win battles rather than records, the HE-100's revolutionary design became its fatal weakness, relegating history's fastest fighter to the shadows of what might have been.